Hi group. I thought it might be helpful for those of you who can't make it to class or those of you who want to review if I went through the slides and just highlighted where you should do some reading and where we talked about some examples. So this is the March 23rd, Monday, March 23rd slides. And so one of the things I want to highlight here is, if it's not clear by now, when you're approaching kinetics problems, you can either use Newton's second law, and that's chapter 12, work energy theorem, and that's chapter 13, the first two sections, and then impulse momentum, which is the second two sections. And so this is what I've been trying to get at, and that is that when we're dealing with velocities and displacements, we're relating work and energy. When we're dealing with forces and acceleration, this forces summing to mass times acceleration is very helpful. And we're dealing with velocities in time, you see that showing up in impulse momentum. So just a high level overview. And this is all related to the reading. So I'm not going to go through each of the slides, but I am going to show you. So this is slide 4, and it's defining impact and the different types of impact. And so when we're talking about direct impacts, you have this deformation phase, and we can relate the incoming and outgoing velocities both by conservation of momentum and by the restitution coefficient. And so ultimately this derivation from the textbook compares that integral of the deformation force over time and the integral of the restitution force over time. And that ratio is related to the loss of energy in the impact. So you lose energy, but you don't lose momentum. And that's how we have our two equations. We have coefficient, or the conservation of momentum, and we have the coefficient of restitution. So in oblique impacts, what we have to deal with is the normal direction to the plane of impact. So we only care about the direction of velocity in that, that line of impact. The other direction doesn't change. So it's exactly the same as a direct impact, except that you only look at the components along the line of impact. So that's really the only difference. And so there are some examples in those slides. Oh, we're not quite at the examples yet. But here we go with a sphere striking a ramp on rollers. And you can think about how you have these velocities in the line of impact, and we can consider how the horizontal momentum is conserved and how the normal components of momentum are relating this along the line of impact. And then the last bit that that comes from chapter 14, a little bit of chapter 14, it's a little bit at the end of chapter 13. It's generally when we have multiple bodies in a problem. So this here is identified at the chapter 13 end, but it's not that different here. So in this case, we just consider how we're getting through the analysis. So we have conservation of energy to get A down to B. We have impact to deal with A striking B. We have conservation of energy, getting B up from A. I've got a little bit of background noise. I'm hoping you can still hear me all right. There is a responsible adult responding to it, which is why I don't sound panicked. And this is a sample problem. So we throw a ball against a wall, and what we have is the velocity in the direction of the line of impact, and we have a velocity that is in the opposite direction. We're given an angle and a coefficient of restitution, and so we're going to have to resolve into components, and this last piece is an interesting piece that might make you scratch your head a little bit. But ultimately, what we want is the momentum of the wall. We deal with it by saying the wall velocity before and after the impact is 0. And so we will deal with that coefficient of restitution as the relative velocity of the ball leaving the wall. So, so you can step through these, and I encourage you to do so. I encourage you to try out the problem and see how your method compares here. And then these reflect and thinks help you kind of apply this a little bit further. So again, this is for you to read, but I want to highlight the sample problems. 20, excuse me, deals with 2 moving objects rather than a ball hitting a wall. We have 2 identical frictionless balls before they strike each other, moving as shown. We have a coefficient of restitution. We have our angles. And this is the same practice. So we use conservation of momentum and coefficient of restitution. And so you can step through this and see how your answers relate. All of this is provided in the PowerPoint slides. And so the third sample problem here is number 21. And B is hanging from a cord. A is released from rest. It is tangent to the cord and stays as such, and then it strikes B. So we're working with a perfectly elastic collision. What happens to each ball immediately after impact? And you'll notice no information specified in numbers, so this is a symbolic solution. So what's the orientation of the impact line? You're going to have to look at the geometry. The momentum of ball A tangential to the contact plane is conserved. That's not changed by the impact. Horizontal momentum is conserved. Relative velocities along the line of action are related by our elastic coefficient, or excuse me, restitution coefficient. And then we can figure out the velocity of ball A along the line of action and the velocity of ball B, which is horizontal given that it is tethered at the end of an inextensible cord. Okay, so you can step through these pieces here, and we can consider the velocities of A, the velocity of B, and alpha is giving us the angle to the velocity of A. This is giving us the angle to the line of impact. So, so I want you to take a look at this and see where your questions are. Okay. The last one here gives us a mass hitting a platform on a spring, and there's a perfectly plastic coefficient, which is to say the mass does not bounce. Okay. And so this is a nice perfectly plastic coefficient example, and you can analyze it as such. We have conservation of energy to figure out how fast it's moving as it hits the platform, and conservation of momentum to figure out how fast it moves after it hits the platform. And then we have conservation of energy once again to relate the kinetic energy of the system as it's starting to move at V3 to the deformation of the spring. Okay, we did this problem together in class, so this will wrap up this video. And the problem was we had a mass A on the slope, and it was attached to a spring that was compressed by 1/10 of a meter. We had another distance, G, down to ball B, and B is tethered here, so B has to move horizontally. So you can kind of break this into 3 motions, where A strikes B, where B leaves the collision, and then where B reaches up to a rotation of alpha. And what we're looking for here is the speed of B and the tension in the rope as it reaches an angle of 40 degrees. So The suggested method that we used in class, we use work energy to get A all the way to B. We use conservation of momentum and coefficient of restitution to deal with A striking B. We can use work energy to get B moving at alpha, and then use Newton's second law to find the tension in the rope. The only piece that this doesn't mention is using Newton's method to find the friction of block A on that contact surface. So, so that's what's shown in the first slide here, and you can take a close look at this. A reminder that the book uses T for kinetic energy, U for work, and then this really should be U, but they describe the work done by gravity as the potential energy due to gravity, and the work done by the spring is the potential energy due to the spring. It's a fine way to note it. It's not wrong. It's just a little bit different than what we talked about in class. Oh, I missed this last bit. So then we can solve that for velocity. And this is using conservation of momentum and restitution coefficient to solve for our velocities after the impact of A striking B. The motion from 1 to 2 of B is conservative, so we can use not work energy, but rather conservation of energy here, where the kinetic plus potential at 1 equals the kinetic plus potential at 2. I recommend you set 1 as 0 potential energy, and that's how we find the velocity at 2. And then finally, the reason why the tension is at, well, the reason why we're going to use normal direction is because the tension here is going to be a result of the weight in the normal direction in addition to the normal acceleration. So we have both of those to deal with. So, so we can find the normal acceleration using the velocity and the radius, which is the length of the chord. And then we can find the tension using the summation of the forces in that normal direction. And then the very last association here is what happens if we change the coefficient of restitution, if we change the rope length, if we change the coefficient of friction, if we change the mass of A. And so give that some thought. And that kind of wraps up our video today on the content from March 23rd.